Okay, let's start. And our next speaker is Francesco Moriello from Zurich. He's going to tell us about power series and computation of multi-loop and multi-leg integrals.
Yeah, thanks a lot, Anastasia. Thanks a lot for the invitation. It's a pleasure to speak here. So actually, this talk is based on a number of papers that appeared recently, and in particular, this one about the computation of two-loop pentagons with one-off shell leg appeared today. So everything is quite fresh. So let me start with a relatively general introduction. So we know that if we want to compute cross-sections or more generally scattering amplitudes in perturbation theory, we need to compute in general a large set of Feynman integrals. So, and I think that this is one of the main bottlenecks for making precise predictions for the LHC, for example. And I think also that it's fair to say that even though much progress has been made in the understanding of these objects in recent years, this is still an open problem and an active field of research. All right, so let me first discuss what is the state-of-the-art technology that we have at our disposal to tackle this challenging problem. So mainly there are two approaches. So the first one is the analytic approach. And the idea here is very simple. So we first identify a space of special functions in general, which are well understood mathematically. And we try to express these integrals in terms of these functions. And there are several ways of obtaining this kind of results. For example, direct integration of Feynman parameter or the differential equations method. So actually the main one of the practical advantage in having representations in terms of known functions is the one that typically we have very efficient numerical routines to compute them, which is of course fundamental if we want to perform predictions that we can then compare with experiments. On the downside, this is a difficult problem. So I would claim that this is not algorithmic. So in general, we don't know, given a Feynman integral, what is the space of functions that we need, and even if we knew, we don't know how to systematically go on this representation. On the other hand, the numerical methods follow an orthogonal approach. So given a representation for our favorite Feynman integrals, we try to directly numerically evaluate them, typically by using Monte Carlo integrators. And there are several available codes to do that based on sector decomposition. And actually, more recently, also the loop tree duality approach, which seems very promising. So the advantage of these methods is that they are, roughly speaking, algorithmic, in the sense that you can use your favorite code, you press a button, and you obtain the value of the integrals in a particular kinematic point. The downside is that typically these results have relatively low precision, and moreover, they require a long evaluation time. So they are not ideal candidates if we want, for example, to perform a Monte Carlo phase space integration. So it's clear from this analysis that ideally what we would like to have is an algorithm for efficient numerical evaluations. And by efficient, I mean something that can be then used to do Monte Carlo integrations and then eventually obtain cross sections. All right, so the starting point of what I'm going to tell you more precisely in a minute is the differential equations method. So in order to set up the terminology, let me basically just give you a couple of definitions. So I will be referring to scalar Feynman integrals in dimensional regularization. So we know that these integrals are not linearly independent, but they satisfy many identities between themselves, which are known as integration by part identities. And one important consequence of this is that we can then identify a basis of integrals known as master integrals. And probably the most important consequence is that this allows us to define a system of first-order linear differential equations for the master integrals that in total generality have this form. So roughly speaking, these equations are defined by a matrix that depends rationally on the dimensional regulator and on the kinematic variables you have in your problem. So in general, solving these equations is very complicated, and also in practice for complicated processes, if you want to save this in a file, so to say the file can be rather large. So in principle, they involve rather complicated expressions. But some years ago, we learned about a conjecture that states that Feynman integrals admit a so-called canonical basis, such that the differential equations can be simplified and written in this form, which is known as the canonical form. And actually, the main feature of these equations is that the dependence on the dimensional regulator is factorized. And one consequence is that it is then algorithmic to write down a solution in terms of iterated integrals, chain iterated integrals to be more precise. Nonetheless, if we want to solve these equations in terms of known functions, this is, for example, multiple Poidt logarithms, this is a much more difficult problem that is not completely understood for the most general set of equations. So what is the main idea behind this talk? So the idea is the one of giving a set of integrals. We want to bypass this function step, which is complicated in general, and we want to land directly to a representation that is useful for numerical evaluations. And what we will do to obtain this kind of results is to start from our set of differential equations and series expand them in a rather peculiar way, as I will show you in a minute. So, of course, I have to say that so series solutions strategies are not new in the literature. Nonetheless, they've been mostly used for single-scale problems, and probably one of the most spectacular results using this method has been the computation of the n-cube leading order cross-section for the X. If we have general scales, the problem is much more complicated. And the reason is the following. So typically what has been done has been the expansion only with respect to one parameter that characterizes a particular kinematic limit. On the other hand, the dependence on all the remaining variables is still exact. So what you get is a series of this form, so a sum of terms where the functional dependence on the expansion parameter is trivial. On the other hand, the coefficients here of the series are still special functions. So in principle and in practice, it's complicated to obtain these representations, and moreover, if these are complicated functions, could also be complicated, for example, to perform analytic continuation in different kinematic regions. So from this analysis, it's clear that in the multivariable case, it would be desirable to have an approach that is systematic, still based on this powerful technology of obtaining power series solutions, and that allows us to obtain results in all kinematic regions. All right, so what is the key idea? So the key idea is to reduce a given multi-scale problem to a single scale and then series expand with respect to the residual variable. So let me be a bit more specific. So we start from several sets of differential equations. We have a set of differential equations for each Mendelssohn variable. And then what we do is to take 2 points in the kinematic space and we fix them. So one point, I'm assuming that is a point where we know the value of the integrals. And another point is the one where we want to compute the value of the integrals. So the first step is to define a contour connecting these 2 points. And this is very simple. So what we do is to just express our full set of Mendelssohn variables in terms of this parameter t, which is the contour parameter. And notice that at this point, t is the only variable around. So everything else has been set to numbers. So SA here and SP are just 2 lists of numbers. And once we have done this parameterization, it is easy to define the differential equations along the contour. So this is a very simple exercise. It's just a matter of applying the chain rule. So now we have a one-dimensional set of differential equations. And the idea is the one of transporting the solution from the known boundary point to the target point that we want to compute. So let me stress already here that this will have to be done on the fly then for every new point. So for every new point I want to compute, I will have to redefine my differential equations along the new contour and series expand around this new contour. But I will show you later that this can be done in a very efficient way. All right, just to give you a more technical idea about this method, so let me start discussing how we find a series solution around one generic point of the contour. So this could be either a singular or a regular point. So I will do that in the canonical polylogarithmic case, which is very pedagogical and also very easy to implement. And then I will discuss briefly the general case. So formally, we have that the solution, order by order in epsilon, is just an integral of the right-hand side of this equation. So the first step is the one of series expanding the differential equations matrix A around the point of interest. Then we just plug this expansion into this formal solution. And then once we have done that, we immediately realize that we only need to consider integrals of this form. So integrals of logarithms rise to an integer power times a monomial. And then, of course, these integrals are elementary, can be done analytically, and the result is immediately your power series centered at the point tk, so the generic point. So this could be, again, a singular or a regular point. If it's a regular point, this sum will collapse to an ordinary Taylor series. And now, of course, by construction, these coefficients defining the series are just numbers. So this is just an example, which is very nice and elegant for the canonical case, but this approach is not limited in any way by the form of the differential equations. It works also for generic differential equations, in particular if they are coupled. And in this case, we can use the Frobenius method to obtain series expansions of this, well, very similar to this one for the canonical case. And so this is a standard method, is discussed in many standard textbooks, I would say. So I just discussed then how to obtain a series solution around one point of the contour. But of course, this series will have a limited convergence radius. So in particular, this series will converge only up to the closest singular point. Then in order to cover the entire contour, we will need to perform several expansions. And there is another subtlety here, is that of course in practice, we cannot deal with infinite series. We will always consider truncated series. So that in order to ensure fast convergence, what we'll do is to set the radius of each of these series to be half the distance between the expansion point and the closest singularity. So schematically here, you can see what is done on a more or less generic contour. So we first expand around the singular points, but then since in general, these singularities are not equally spaced, there will be possibly some uncovered segments of the contour. So what we do is just to expand also around regular points in such a way that we cover the entire range. Okay, so there is an important point here is that, of course, these series have been obtained by differential equations. And as we know, a given solution from a differential equation will be only determined up to a set of constants. But then here I'm assuming that one point is known, is our boundary point. So this first set of values will fix the constants for the first series around the contour. And then by continuity, imposing continuity, when we go from one series to another, I'm able to fix the constants for all the series. And in this way, if we formally set to 0 the series outside the radius of convergence, we can define the solution along the entire contour in, well, we can break down the solution along the entire contour in this way. So once we have done this, we can compute the value of the integrals at any point of the contour, in particular at the target point that we are interested in. So now there is an important issue, which is of course the analytic continuation. So we know that Feynman integrals are multi-valued functions. So in general, we need to perform analytic continuation. But in this approach, everything is completely straightforward. So the solution, in particular the solution around the physical threshold, will have this form, where now I'm assuming that tk is the value of the contour parameter corresponding to the physical threshold. And then we have that the only two non-analytic terms are a logarithm and a rational power here. So how we do the analytic continuation? Well, okay, as I said, let's assume that tk corresponds to a threshold, let's say in the Sn channel. And then we know that Feynman prescription dictates to add a small imaginary part to Sn. But of course, in the series, by construction, we no longer have the information about the various invariants. So actually this cannot be applied directly anymore at this stage, but we immediately see that this prescription induces a prescription at the level of the t parameter. And so by applying this prescription, we are able to analytically continue all the non-analytic terms of the series, and this gives us the right prescription. So there is a subtlety here that I don't have time to discuss, and is the issue of overlapping singularities. This can happen, which actually means that for a given tk, I have multiple channels going on threshold. But in practice, it's very easy to avoid this problem. It's just a matter of choosing a new contour to reach the target point. So this fixes this apparent complication. All right, so now we can discuss applications. So this is the paper I was mentioning before. In this paper, we computed the full set of master integrals in the planar case relevant for the two-loop 5-point corrections to one-mass processes. So more specifically, these integrals are relevant, for example, for vector boson production plus 2 jets. And mathematically, this is a very challenging problem. So one reason is that it depends on 6 physical scales. So what we did was the following. So we first defined our differential equations for a D-log basis, so that the differential equations are much more compact and manageable. However, at least for the moment, an analytic solution for these equations seems to be out of reach. And probably the main reason is that the alphabet of these equations depend on a set of 3 square roots that cannot be rationalized at the same time. So this is a technical complication. On the other hand, the series solution is fully algorithmic. So as I'm going to show in the next few slides, we obtained results in all kinematic regions, and the boundary conditions could be fixed just by requiring regularity conditions of the solution. So more specifically, we imposed the absence of spurious logarithmic singularities in the Euclidean region. All right, so one way to show the efficiency of this approach in practice is to show plots. So here I'm showing 3D plots for a sample pentabox integral at weight 4. So here you see the real part and the imaginary part. And this plot is done over a 2-dimensional slice of the physical region. So the physical region looks like this. We fix the values of all the invariants except these 2. And actually this slice is unbounded. So in order to present the plots, it's convenient to map these to a finite region, in particular with a variable change. So its form doesn't really matter here. You can map this to the unit square so that you get a compact domain for these plots. And we can see actually some feature. We can recognize some features already. So as you can see, this region touches the physical threshold S34 equals 0. And this is reflected in this logarithmic divergence here. Actually, here you see there is a very fine structure. Nonetheless, it's straightforward to resolve this by using our approach. And so this is just a zoom in of this structure. And then this enhancement that we see on the right-hand side of the unit square is related to the point at infinity. And let me also mention that to obtain these plots, we sampled the integrals over, roughly speaking, 500,000 points. So of course, in order to do this, you need something that is quite efficient, but this is totally doable. So another way of showing the efficiency is, of course, just to show high precision numbers. So I didn't mention it before, but this is in general the case when you solve single, well, one-dimensional problems. And it's the one that you can, in principle, obtain arbitrary numerical precision just by increasing the truncation order of your series. So here I have a sample collection of pentabox integrals. Actually, these are, there is one pentabox integral for each of the 3 two-loop families we considered. And I show here 128 digits in this physical point. All right, so as I mentioned before, this approach is not limited at all by the form of the differential equation. So it works also if the result is expected to be beyond polylogarithms. And in fact, we could use it to solve the full set of master integrals for the two-loop QCD corrections of X plus Z production, retaining the exact mass dependence on the internal heavy quark and the external X. And so this is, so the practical results is that with this computation, the full set of master integrals required, for example, to compute the next to next leading order X inclusive cross-section in QCD, retaining the bottom and top mass dependence is now known. And this is actually also thanks to this recent work by Chacon and collaborator, where the corresponding three-loop form factors were computed. All right, so this is the slide that characterizes the typical timing and precision of this approach. So let me start here with this first table, where we show the time to compute, well, the average time to compute one master integral in one physical point, up to 84 on one CPU thread. And here I'm considering quadruple precision, so already a relatively high precision. And as you can see, the timing is of the order of 1 second per master integral. And this time has been obtained by averaging the timing over, roughly speaking, 10,000 Sherpa Monte Carlo phase space points obtained by computing corresponding leading order cross-section. So in this second table here, on the other hand, I show the same timing, but for this elliptic family, for X plus Z, that we call family A. Again, the timing is of the same order of magnitude, 1 second per master integral. But here I also put a comparison with SecDec and Fiesta. Actually, here the run was done with, of course, a much lower precision, a relative precision of 10 to the minus 2. As you can see, the timing per master integral is at least 2 orders of magnitudes larger when using these codes. And then finally, what probably I find the most interesting comparison is how this approach compares to having a fully analytic result of some form. So this could be done only for this family, which has been computed a few years ago by this collaboration in terms of multiple polylogarithms. So we could actually compare the timing. And as you can see, and we did a comparison with very high precision, so with 128 digits. As you can see, with our approach, it takes on average 16 seconds per master integral. Using the polylogarithmic expression, it takes, roughly speaking, 82 seconds. And actually, this kind of difference holds, of course, also for lower precision. So there are two take-home messages in this slide. So the one is the timing that we observed by studying several families, not only these ones, which seem to be sort of an invariant. So we always get something of the order of 1 second per master integral with quadruple precision on one CPU thread. And another consideration is that the timing and the precision seems to be comparable with the generic fully analytic result in terms of polylogarithms. So of course, this comparison.
Francesco, there's a question. Sorry, Francesco, there's a Lance has a question.
Yeah.
No, I meant the question at the end of the talk.
Yeah, I'm almost done. So okay. Yeah, I was about to stress an important point, that this kind of comparison has to be taken with care, because we know that a polylogarithmic expression admits several different representations that are that can be optimized for numerical evaluations. However, obtaining this kind of simplifications for complicated polylogarithmic results can be very challenging and is not algorithmic in general. So I think this kind of comparison is still interesting, even though I warn you, should be taken with care. So this brings me to my conclusion. So we discussed a systematic method to compute generic Feynman integrals based on the series solution of differential equations. And we observed that this method seems to be very efficient and suitable for phase-space Monte Carlo integrations. And moreover, we presented several new results for complicated integrals, which are at least for the moment, out of reach for analytic methods. So for these reasons, we are relatively optimistic, and we believe that this method will have an important role for the computation of several LHC observable in the near future. So that's it. Thank you.
Thank you. I know we have time for questions. Lance?
Yeah, very nice talk, Francesco. I was just wondering if you might be able to make it even more efficient by caching your results. I mean, you're going all the way along this line and you're collecting a lot of data on the way. Why don't you store the values and eventually build up a grid over the phase space that allows you to not have to go as far each time?
Oh, exactly. That's what we do in practice. I just didn't have time to discuss this. So basically, yeah, you're totally correct. What we do is so what you do in practice is that as long as you compute and collect data while you are computing several points, for example, with during a Monte Carlo integration, what you do every time is to choose as a boundary point the closest point to the target point. And this is, of course, much better because typically when you have close points, you need fewer segments to compute, to patch the entire contour, and then of course this becomes faster. And actually, I think I don't have the plot here, but actually you observe a speed up. So you observe that as long as you collect points, you see that the average evaluation times goes down with the number of points already evaluated, and then it approaches an asymptote, roughly speaking, after 10,000 points. So yeah, that's what we do.
More questions? So if you have a question, please raise your hand. Also, could you please use your real name, because it's hard for me to call on people. So Matt has a question next.
What I was curious about, you mentioned that that in this case there's an unrationalizable alphabet. I'm curious whether if you sort of maximally rationalized it in some sense, would the remaining irrationality end up as elliptic or is worse than elliptic?
Okay, so for this, first of all, for this planar family, which is the one that we looked at, we have a D-log set of differential equations. So here we believe that the answer would be somehow in terms of polylogarithms, even though it's not manifest at the level of the differential equations, just because we have square roots and we don't know how to rationalize them. So concerning what we actually did, if I remember correctly, because actually, so once we saw that we could obtain basically a very efficient representation of the result, we sort of reduced the priority of obtaining a polylogarithmic expression. I think what we managed to do was to rationalize 2 out of 3 square roots, but then you're always left with a residual square root that of course complicates the analytic solution. So this is what we do.
Thank you.
Right, so we have a question, Kostas. Kostas, could you please unmute yourself and ask?
Yes, okay, thank you very much. So, good afternoon. So, I would like to ask the following. This comparison you saw with our result, in a physical point or it is in a Euclidean point?
Physical point.
So just to be very brief, if you allow me, 1 second. So our representation, as you know, is based on working with an extra parameter and doing the differential equation with respect to that. And this is, in a sense, based on Euclidean region. So if you would like to go to the physical region, what we provide in our result is essentially a numerical way of doing this by adding to the invariant some small imaginary parts. And from the point of view of GNAC, this of course is very hard to evaluate. So we did the same exercise with 2 things we have done already and compare with, let's say, results by Johannes Hem. And if you take this into account, doing some vibration basis properly, then putting the expressions in an analytic form in the physical region, this is surely very much different in timing.
Yeah, sure,
So
sure.
therefore I would wait for a couple of months when we finish your calculation analytically, and we can compare this all together.
Yeah, of course. I totally agree. Indeed, this is why I stress the fact that this comparison has to be taken with care. We did it mostly just to have an idea of what we are talking about, what is the rough performance of our approach. And indeed, I can, of course, confirm what you did or what you're saying. So what I showed before here, it's an average evaluation time. So we considered 6 scattering regions, and we computed 1 point for each region using your representation. So, and okay, first of all, the analytic continuation was done numerically in the sense that by hand, we added a small imaginary part to the invariance to get on the right side of the branching points. But then on the top of this, we observed indeed large fluctuations concerning the evaluation time. So there was one region that was considerably faster than the average evaluation time. And if I remember correctly, actually in that region, the timing for your result was slightly below our timing, comparable. I think it was something like 10, in our case was 16 seconds per interval. But then we observed large fluctuations. As soon as you go to another region, the timing would become much worse. And then of course, this is why you have an average time that is overall this much larger than our timing. So yeah, but thanks for the observation. Yeah, I totally agree.
Let's see, are there more questions to Francesco? So again, please raise your hand, or you can type them in the chat, and then you can unmute yourself. No? All right, if there are no more questions, let's thank the speaker again.